Hello everyone, let me welcome you to our interview series. In today's session, we will see what are the different classification of materials. We already know that materials can be classified as metals, ceramics, polymers and composites. But there is another classification of material based on how the property is going to change with respect to direction. So here we have three types of material. One is called as an isotropic material, second is called as an orthotropic material, and last one is called as an anisotropic material. Let's have a detailed look at each of them one by one. So in case of isotropic material, properties will not change with respect to the direction. So if I consider any material, then at any point inside the material, the properties are not going to change with respect to direction, as you can see in the figure. In all the direction, property will remain the same. Common examples of isotropic materials are metals and glass. In order to completely define the properties of isotropic material in any FEA software, you will require at least two independent elastic constants. As we know, we have the four elastic constants: Young's modulus, modulus of rigidity, bulk modulus and Poisson's ratio. So out of these four elastic constants, you will require to define any of the two. Next, we will look into the orthotropic material. Here, one important point you should remember: the orthotropic materials are the subset of anisotropic materials. In case of orthotropic material, properties will change with respect to mutually perpendicular direction. So if I have to give the example, let us consider any material. Inside that, if I consider any point, then properties at this point are going to change with respect to mutually perpendicular direction. As you can see, here Young's modulus is changing with respect to the direction. Common example of orthotropic materials are woods and composites. In order to completely define the orthotropic material in any FEA software, we will require 9 independent elastic constants. Now let's move on to the anisotropic material. These are the material in which properties are going to change in all the direction along the object. So if I have to give the example of anisotropic material, then at any point, since the properties are going to change, you have to define the properties along every important direction. So as you can see over here, properties are changing along every direction along the object. Common examples of anisotropic material are woods, composite, biological tissues. Another popular example of anisotropic material is a sheet metal formed by squeezing the thick section of metal between the heavy rollers. Because of this squeezing action, the grain structure gets flattened as well as it gets stretches. As a result of this, material becomes anisotropic because its property is going to differ in the direction in which it was rolled and other two transverse direction where it was not rolled. This particular method is used as an advantage in the structural steel beams as well as in aluminum aircraft skins. In order to completely define the anisotropic material, we will require 21 independent elastic constants. Here you might get confused and ask, wood and composites are both orthotropic and anisotropic. How it is possible? As I told you, orthotropic is a subset of anisotropic. In case of orthotropic, properties are going to vary in mutually perpendicular direction, and in case of anisotropic, properties are going to vary in all the direction along the object. So that's why the woods and composite are both orthotropic and anisotropic. In interview also you can explain the same. Now to give you the proper feeling of these material properties, I have opened the ANSYS Workbench. Within ANSYS Workbench, we are going to define the engineering data. Now here let us create a material calling it as a wood. Now since we know that wood is orthotropic material, from the toolbox, here we have the linear elastic, and under linear elastic, here we have to define which type of material it is. So in case of isotropic, you will require to define only two elastic constant. So if I double click on this isotropic elasticity, as you can see, the same property has been updated in the properties outline, and there are two boxes which are in the yellow color. That means these two properties are required to define at any cost. Now since this was the isotropic elasticity, we require to define two properties. But let's see what will happen if I define this particular wood as an orthotropic property. So let me delete this one. Again, I will double click on orthotropic elasticity. Now as you can see over here, I have to define the 9 properties. So Young's modulus in X, Y and Z direction, as well as Poisson's ratio and shear modulus along the planes. Now let us see what will happen if I define, instead of orthotropic, let us define the wood as an anisotropic material. So double click on anisotropic, and as you can see in the table properties outline, here I have to define the 21 properties. So I hope you get the proper feeling of what are the classification of material. based on the direction of variation of property. So prepare this question properly, because in some of the interview they will directly ask you this question, or even if you are working in the companies, if client ask you to give the orthotropic material for the component, so you should know which properties you are going to ask the client for the material.